When the e-commerce platform ShopEasy first launched, it ran its entire business off a single physical machine sitting in a data center. For customers to access that website, the server needed a unique identifier on the network, an IP address. Think of it like a physical street address, letting outside computers know precisely where to send their data. But an address alone isn't enough to cross between different networks. That requires a router, which acts as the digital post office, sorting and forwarding packets of data from one neighborhood to another until they reach their destination. Since humans don't want to memorize long strings of numbers, the internet uses the domain name system, or DNS. It acts as the ultimate phone book, translating a human-readable name like shopeasy.com into the exact IP address of the physical server. This simple physical setup worked for the early web, but it created a single point of failure that could take down the entire operation. If a holiday sale brought a sudden spike in traffic, that solitary machine would become overwhelmed. It would crash, and the entire business would go instantly offline. The common workaround was to buy excess hardware just to handle those busy days. The problem was that for the rest of the year, those expensive machines sat entirely empty, wasting the company's budget. Adding more capacity meant racking, wiring, and maintaining rows of heavy physical equipment. The internet was growing too fast to rely on physical metal. To survive, engineers had to find a way to scale their software without constantly buying more physical boxes. The solution was a software called a hypervisor. It slices one large physical server into multiple isolated virtual machines, each acting like a fully equipped independent department. To let these VMs communicate safely, they are assigned private internal IP addresses. When a VM needs to talk to the outside world, it uses network address translation, converting those private addresses into one public-facing IP. Virtual machines eliminated hardware waste, but as applications grew, companies suddenly found themselves manually configuring thousands of these boxes, creating an overwhelming administrative burden. To shed the burden of maintaining hardware, companies shifted to the cloud. They stopped owning servers and started renting massive pools of computing resources from expertly managed data centers run by providers like AWS. To maintain security inside these shared facilities, businesses carve out a virtual private cloud, an isolated corporate wing dedicated exclusively to their own traffic. Within that VPC, network spaces are divided into subnets. Web servers are placed in a public subnet, while sensitive databases are hidden in private subnets. At the doors between zones, security groups act as digital bouncers, ensuring only authorized packets cross. But there was still a bottleneck. Even with vast cloud resources and tight security, the applications running inside were massive, monolithic programs. Updating them was slow and often required taking the entire service offline. Developers solved this by breaking those massive programs down into microservices, specialized independent tasks like processing payments, managing shipping, or loading the catalog. To deploy these microservices anywhere, they are packaged into containers, lightweight toolboxes holding only the specific code and dependencies a service needs to run instantly. This shift created an entirely new networking challenge. Because dozens of containers are buried inside a single virtual machine, the software builds internal network bridges to let them talk to each other, and to let the outside internet reach them, engineers rely on port mapping. This explicitly forwards an external request from the host machine's main entrance directly down into the specific container's port. Containers gave developers fast updates, but manually tracking these components, mapping their internal network ports, and routing their external traffic quickly outpaced human ability. To control the chaos, the industry adopted Kubernetes, acting as a master city planner. It automatically tracks, places, and restarts massive swarms of containers based on real-time traffic demands. Kubernetes solves internal routing using the container network interface. It automatically plugs a virtual cable into new pods, assigning them unique IPs. Because these IPs change constantly, an internal DNS acts as a static phone book, letting services search by name instead. For outside traffic, the ingress controller acts as a smart receptionist. It reads incoming requests and directs them straight to the correct internal microservice. By automating the underlying network labor, Kubernetes removed the manual configuration bottlenecks that previously limited how fast a system could grow. In the modern era, millions of containers are spun up and destroyed in milliseconds across vast global networks. But if you peel back the complexity of a modern cluster, stepping backward through the microservices, through the containers, and past the virtual machines, you will still find a physical server underneath. Despite decades of evolution, layers of hypervisors, and automated orchestration, the actual rules of the internet have remained consistent. Everything still relies on the same core requirements. Devices need addresses. Traffic requires specific routes to follow. Names must resolve through DNS, and security rules must dictate what is allowed through the door. Mastering these foundational building blocks gives you the ability to confidently navigate any system, from a physical machine in a closet to a massive global cloud cluster.